This is a production of Cornell University.
We are going to change to a different perspective. So far we've been talking mostly about soil architecture. What's there? What do you see? Okay? What's the distribution of it? Today I'd like to shift us to stuff that we don't see. Process-driven stuff. And we're going to start, actually, this is kind of strange, we're going to start process-driven stuff with an artifact or a solid material, and we're going to start talking about colloids. Clays, really. Colloids are things that are really, really small. Okay? And there's basically 4 types of colloids when you start talking about soils. But we're really talking about things that are real small, and basically the definition for a colloid is something smaller than 1 micron. Okay? Which is kind of interesting because the size break for clay is 2 microns. So basically, by default, we think of anything as clay sized or smaller. Okay? Now, size is the definition. But if I'm talking about small things in certain volumes, we certainly need to start talking about or coming back to this idea of surface area. As things get smaller, this is a question in the prelim, as things get smaller per volume, what's going to happen to the surface area? Surface area is going to increase. Okay? And when we start talking about surface areas increasing, we start talking about lots of things. This is that edge. Things are going to be happening at the edge. Okay? And when we talk about colloids, we're generally talking about, there's a couple other things we talk about. We're generally talking about surface charge. These particles are charged. They have a charge associated with them. And if they're a charged particle, they're going to interact with other charged particles in the soil. Now, interestingly enough, the nutrients, water molecules, basically everything that's moving in that volume is a charged particle, which means this charged surface has a huge role. Now, with soil colloids, it's generally negative. The charge is generally a negative charge, but it's not always. Okay? And if it is generally negative, we're rarely talking about cation absorption. Adsorption versus absorption. So it's on the surface. It's not being absorbed into its contact at the surface. Now, it's generally positive, generally negative. The cation is a charged ion. It's a positively charged ion versus an anion, which is a negatively charged ion. Now, if this is generally negatively charged, positive ions are going to be sorbed onto the edges. But it's not always negatively charged. Sometimes it's positively charged. And if it's positively charged, we're also going to see anion absorption. And the truth is, both positive and negative charges are usually present at the same time. Okay? All right. So the types of colloids. There are basically 4 that we're going to be talking about. And actually, we are going to talk about all of these. The first one is crystalline or silicate. These are sheet silicates, okay? Clays. Okay. We also have non-crystalline silicate clays. These are not sheet clays. When I'm talking about sheet clays, anybody know what this is? This is mica. I'm going to pass this around in a few minutes, but basically this is a layered mineral. The layers in here are basically based on silica and oxygen. Okay. We also have iron and aluminum oxides. Remember, we're talking about colloids. We're talking about small things. Okay? These are dominantly gibbsite, the aluminum oxides, or goethite, the iron oxides. Okay? And we're also going to be talking about organic colloids, humic material. Okay? These are non-crystalline colloids. They're dominated by long carbon chain molecules. Okay? Today, we're going to be talking about the top one. So when we start talking about sheet silicates, crystalline silicates, I thought I should show you guys some pictures and give you an idea that not all of these are the same. And we're going to be talking about how these things change based on their mineralogy. But first thing we're really going to be talking about is how these things are built. Okay? This is a kaolinite, fairly small, flat. This is a 2 micron bar here. This is a 2 micron bar here, just to give you some references. This is a kaolinite, fairly small, flat, almost perfectly hexagonal in some cases. Here's a smectite, a lot larger but curved, a lot of shape there, rounding, okay? And that has to do with how these silicates are put together. Okay, what is in these silicates has a huge influence on its charge and its shape and its size and its weathering ability. I threw this one in here. You guys see the dark water in here? Okay, I don't know where I pulled this from, but this dark water in here is basically organic acids. It's organic material. Okay, that organic material, these long carbon change molecules, these as well are colloids. I threw this one in here. This is just sort of a throwaway slide. It's actually it's from your book. This is not a real molecule, but we throw this molecule up here to give you an idea about the complexity of these organic molecules. Okay, lots of carboxylic groups, lots of phenolic groups, a lot of carbon ring structures. This is not a real molecule, but it just gives you an idea of the diversity or the complexity of these materials. Okay, but today we're going to be talking about phyllosilicates, sheet silicates. Okay, and when we talk about that, we really, just sort of drive home a point that we're really talking about size. Okay, this is the relative amount, and this is the particle size, and this line basically represents the break between the relative amount of primary minerals. These are silicate minerals as well, to the secondary minerals. And you can definitely see the size break someplace right around here in that 2 microns. So when we start talking about colloids, we're really talking about these secondary minerals. There are some primary minerals, but we're really mostly talking about secondary minerals. So we're talking about minerals that have formed at the surface of the planet. All right, so what do these things look like? And this is when I'm going to pass this around. These are some slides, some micro slides of some mica material. Okay, that's what this is. Please don't break it up too much, but take a look at it, pass it around. I want you to look at it on the face side, but also look at it at the edge. And you can literally see that it's made up of layers. Okay, those individual layers that are in here, there's thousands of individual sheets, layers. You're just seeing a larger chunk of it. These things are bound together. Okay? And you can sort of see the edge here. You can see the layering that's in here. This is a front on, but you can see that some of it's peeled off. And basically that's what you're going to see. So let's start with the building blocks. How are these things made? Okay? Well, these sheets, these layers that you see, are basically made up of 3 and sometimes 2 and sometimes 4 individual sheets that are made up of aluminum, silica, or silicon, and oxygen. Now there are impurities in there, but let's talk about these as pure molecules at this point. Okay? Here are the sheets. There's a tetrahedral sheet, an octahedral, and a tetrahedral. That's an individual layer. Okay? This layer has a space in between the next layer, and all together we call these things a sheet. A crystal, a micelle, I should say, when you put it together. Okay? Now, each one of these sheets, these individual sheets, are made up of different ions in arrangement. Okay? And they're primarily a tetrahedral arrangement here, and an octahedral sheet here, and a tetrahedral sheet here. In this case, we're looking at a 2-to-1 mineral, and that will mean something to you in a few minutes. But basically, these are bound together in a closely balanced charge arrangement. Okay? Let's talk. Now, so this, I don't think, have you guys seen this slide before? Or something similar to this slide? You guys have seen, I thought I threw it in here. Obviously I didn't. All right. Everybody getting seasick right now? Okay, so here's the combination of sheets. Let's start over here. Here's a chlorite. Okay. Here's a tetrahedral sheet, a tetrahedral sheet, an octahedral sheet. In between the 2 tetrahedral, octahedral sheet, there's a hydroxy sheet. That hydroxy sheet is basically holding this material together. Okay. Here's a non-expanding mica. This is basically what's being passed around right now. The same tetrahedral, octahedral sheets with, right in the middle here is K, potassium, holding those sheets together. Here's a vermiculite, basically the same sheets again, but in this case there's nothing holding it together. Okay, so basically in here we'll have water and other molecules. And then finally we can have a smectite, basically the same arrangement, but in this arrangement versus this arrangement, we haven't talked about this yet, but the charges and where those charges are a little bit different in each of these. And so as a result, the properties of these sheets are different. And then finally, very weathered material where we're actually losing one of the tetrahedral sheets. We have basically a 1-to-1, a tetrahedral octahedral sheet, and we call this a kaolinite. Okay, now what I'm going to do now is we're going to talk about how these things are built, how they weather, and how they change. Okay, so let's go back to magma. Okay, we're going to start with primary minerals. Okay, ions that are dissolved in magma are basically moving like water. They're rapidly moving around. Okay, there's no real regular pattern. But as these ions start to cool, as that magma starts to cool, the ions basically become frozen. Literally become frozen. They become solid, just like ice is frozen. Okay, and when they get frozen, they basically form, now it depends on how fast and what the ingredients are, but they basically form symmetrical crystal arrangements. These ions bond to each other, and they hold their arrangement. Now with phyllosilicates, you have to sort of imagine what is the composition of that soup. And with phyllosilicates, you can see aluminum, silicon, and oxygen are the dominant elements that are in this potential soup mix. And so as a result, these are the dominant elements that are in that crystal. We have two primary building blocks. One is a tetrahedral arrangement. Can you guys see this? Yes, kind of? Should I kill one more bank, or should Jean-Marc kill one more bank? Yes? No? We're good? Okay. And this is the octahedral, okay? And what you're seeing here, I can reach this one. What you're seeing here is you're seeing a central ion here being bound at the peripherals by others. Okay, in this case, the central ion is either an aluminum or magnesium. Let's imagine aluminum right now. These outer ions are oxygen. In this one, we're looking at a silica core with an exterior of oxygen. So if we go back to this pie chart, aluminum, silicon, and oxygen.
This has been a production of Cornell University, on the web at cornell.edu.